Okay, so hopefully you've had a minute to watch the videos from Flippin' Physics. If not, you can go back and watch those about circular motion and the reference circle and all of that stuff. So we're going to go on now and transition into talking about waves. So we've been modeling these simple harmonic oscillators, and now we're going to adapt those to wave motion, which you saw from those videos we can do fairly easily and come up with the equation of motion. So wave motion, we're going to particularly start with mechanical waves. So things like sound waves, earthquake waves, waves on a string, and so forth. Light waves are not mechanical waves. And the big difference between mechanical waves and light waves is mechanical waves need a medium to move through. They need a medium to oscillate in and propagate in, whereas light waves don't need that. They are self-propagating. So the reason a mechanical wave is able to propagate a wave is even in a gas, all the particles are interconnected. They interact with each other. And so that energy is able to move through that medium through the interaction of the particles. So again, to be able to keep a wave going, you need a driving force. So if I just flip a string one time, one pulse will travel down the string, and that's it. That's all that happens. So if I want the wave to continue to create a waveform, I have to drive. I have to have a driving force on that wave to keep generating pulses. So if you go back to the concept of the block and spring, if you think about a wave on a string, each part moves up and down. So this little piece moves up and down, which then causes this piece to move up and down, which causes this piece and this piece. And so what happens is each little individual part of that string is like a block and spring system. It oscillates around its own equilibrium position. Then it's the sum of all of those that causes the waveform. So we're going to particularly look at sinusoidal waves because they're periodic. So sine waves, cosine waves, and again, as we saw from the Flippin' Physics videos, they can be mimicked, they mimic the motion of the block and spring system. So the equilibrium position, again, we're going to oscillate around the equilibrium position of that particular little oscillator. That's usually going to be the midline of the wave. So when we look at a wave's anatomy, they all have the same parts, right? The wavelength is going to be the distance between, in meters, the two identical parts of the wave, okay? And I've got a little cartoon that shows this on the next page. We're going to indicate that with the Greek lowercase lambda. The crest, or the peak, is the high point of the wave, which measures an amplitude. The trough, or the valley, is the low point of the wave, which is also an amplitude. They're equidistant from the amplitude, or they're equidistant from the equilibrium position. They both define the amplitude of the motion. It's just one's on the positive side of the displacement, one's on the negative side. Now, the amplitude will be different things. It may be, in the case of a string, it's meters. In the case of a sound wave, it's intensity. So amplitude may be in different units, depending on what kind of wave you're looking at. Then frequency, we already mentioned this earlier, but it's the number of wavelengths now, because that's one complete oscillation, the number of wavelengths that pass by the point in 1 second, or a particular point in 1 second. Now, so there's going to be different motions going on in a wave. The equations of motion that we talked about in the previous unit looks at the motion of the individual oscillators doing their thing in their little spot. Wave speed is about the wave as a whole traveling through the medium or traveling through space or whatever. So the wave speed equation is going to pay particular attention to the propagation of the wave. So if we have a nice, simple harmonic oscillating wave, it's very easy to calculate the wave speed because it's moving at a constant velocity. Okay, now in, like, say for example, the speed of sound or the speed of light or whatever. Yes, the speed of sound in different materials is different, but within that material, say I stay in the air or I stay in the water or whatever, the speed of that wave is constant until I change the material. Okay, so it's pretty easy to calculate the wave speed. So this is a propagation speed. we just go back to physics 1, good old distance divided by time, simple calculation because the speed is constant. So I have learned that there is a particular distance that I know called wavelength, and the time it takes to move one wavelength is a particular value of time called the period. Okay, so I can just take the wavelength divided by the period, and that's how I can find the wave speed. But it's not always easy to measure the period of a wave, especially if there's, it's a periodic wave and it's hard to look at one wavelength. Another thing that might be easier is the frequency. So since frequency and period are inverses of each other, I can take like a tuner and measure the frequency or whatever. So instead of using wavelength divided by period, I'll just use its inverse and do wavelength times the frequency. So it's a little bit easier sometimes to measure the frequency of a wave than it is to measure the period of a wave. Okay, so the wave speed equation that we're going to use is the wavelength lambda times the frequency f. Wavelength needs to be in meters, frequency is going to be in hertz, which remember is cycles per second. So when I talk about waves, there's basically two types, okay? And I'll put a little video up that'll show the two types. There is, when you draw a wave on the board and you make the sinusoidal function, that's a certain type of wave. So in a sine wave, the oscillation is going to be, say, vertical. So I'm going to wave my arm up and down with a string. But that pulse is going to travel horizontally across the string. So the oscillation direction of the little oscillators and the propagation direction are perpendicular to each other. We call that a transverse wave, okay? So the oscillators are perpendicular to the propagation direction. Light is a transverse wave. Something called an S wave in earthquakes are transverse waves. The other option is I could take a slinky and I can squeeze it and stretch it, and then that pulse would travel along the length of the slinky. So in that case, the oscillation and the propagation are parallel to each other. We call that a longitudinal wave. So a longitudinal wave is something that involves a compression or a pressure, okay? So sound is a longitudinal wave because sound requires the compression of the air molecules or the water molecules that the sound is moving through. Also, P waves in an earthquake are an example of a compression wave. Longitudinal waves require a medium. Transverse waves like light doesn't need a medium. Other transverse waves do, but light doesn't need a medium. So longitudinal waves, you got to have something to compress and decompress, or compress and rarefy is the other word for that. Okay, I shared a couple of the flipping physics videos that talk about superposition, but superposition is where you have waves interacting. Okay, and this happens in all kinds of applications, but the most obvious one is in musical instruments. Superposition is where you have multiple waves on a single medium, so like multiple waves on a string, to combine to form a single, sometimes more complex waveform. And I shared a couple of videos about that you can watch. The way we accomplish this is by interference. Okay, waves that there's two forms of interference. Now, and wave interference is not always all or nothing. Okay, constructive interference just means that they are on the same side of equilibrium when they meet. So the combined waveform that they give you is greater in amplitude than the individual waves. It doesn't mean that it doubles, or it doesn't mean that it's the amplitude of this one plus the amplitude of this one. That's not how that works. So it's a little bit more complicated than that, but constructive interference doesn't necessarily mean you double the amplitude. It just means you increase it. Just like destructive interference doesn't mean cancellation. Okay, destructive interference means they meet on opposite sides of equilibrium, so the combined waveform is less in amplitude than the individual waves. Now that doesn't mean it's zero. It doesn't mean they exactly cancel out. It just means they decrease the overall amplitude instead of canceling out necessarily. There's very special conditions for total cancellation, and that's called total destructive interference or complete destructive interference. Okay, sometimes you get that, but not always. Just because it's destructively interfering doesn't mean that it's zero. Okay. So what happens in musical instruments is you get these complex combinations of waves called standing waves. Now, the reason they're called standing waves, if you saw in the flipping physics video, the actual wave waveforms do move, but the place where there's total destructive interference and total constructive interference stays in the same spot in the medium. So it looks like the waveform is stationary. Okay, and this is what gives musical instruments their particular tonal qualities. So you've got interference either in strings, or you've got interference in air, or you could have light waves interfering. And again, it's what gives us the particular tonal quality. Now, your book is going to show you some very simplified standing waveforms. They can get much more complicated, but the analysis is the same, whether they're simple or more complex. So what happens is the waves appear to stand in position, creating nodes and antinodes. And there is a lab, the PHYS simulation, that you can look at that will demonstrate this. So I'll see if it will work. Okay, so I'm going to put this on oscillate. And I want to slow it down. Okay, and I want to put this in slow motion. Now, what's happening here is you've got an oscillatory system. And if you watch the videos, you saw that when it comes to a fixed end, it's going to invert the waveform. So let me restart this, and you can watch as it moves down. So when this waveform gets down here to this PHYS clamp, it's going to flip. See how it flips and it goes back? So now the waves are interacting with each other. So these reflective waves are interacting. Now, right now we don't have a standing waveform because I don't have it set at the right frequency. So I'm going to turn the damping completely off. And then I am going to increase the frequency. So I'm going to restart it. I'm going to move the frequency. Let's pause for just a second. Okay, I want to move it up to 2 or so. You can never get exactly on there. There we go. All right, so what's going to happen is as these waves interact, they're going to add and subtract from each other. Okay, so see how those waveforms are really large? So a standing waveform would be where this position right here is always constructive, or excuse me, always total destructive interference, always total constructive interference. And that's how they add up. All right, so now this one is not exactly right because you see the amplitude getting smaller here. But that gives you the basic gist of what a standing waveform would look like in the real world. So what that means is I can figure out some things about the tonal quality of that sound, for example, by looking at how many standing waveforms we have. So let me go back now. So you noticed as that continued to run that those amplitudes kept getting bigger and bigger and bigger and bigger. That's a situation called resonance. Resonance is where you have standing waves of large amplitudes created. And there's different ways that you can achieve resonance. So let me show you all this real quick. See if it'll come up. Okay, so resonance happens, let me go down here. Okay, so resonance happens when the driving force is in frequency with the resonance, okay? So if I'm going to drive an oscillation, I need to apply my force at the same frequency that the resonance is occurring at. If I don't, and I'll show you here, if you're going to push your friend in the swing, it matters when you push them. If you push them at just any time, like this guy's about to do while the swing is not in the right frequency, that person's not going to swing any higher and they're probably going to get mad at you. Okay, I'm going to try to reload this and see if that video will show up. Okay, so when you push somebody in a swing, you kind of time your push in frequency with their motion, right? Because that way you're driving them to swing higher and higher and higher. So you're increasing the amplitude of their swing. Now, the lowest standing waveform, the lowest frequency standing waveform that you can get is called the natural frequency, or the first harmonic. And then as you start adding more standing waveforms by changing the parameters of the system, you get what are called the second, third, fourth harmonics, or sometimes called overtones, depending on what book you're in. The natural frequency would be the first harmonic, and then the next one would be the second harmonic, or the first overtone, because it's over the natural frequency. So it's sometimes also called the fundamental frequency. That's the lowest natural frequency that that system can create. So it's the simplest standing waveform, and then the higher orders are the second, third, and fourth harmonics. Now, it's going to depend upon the speed of the wave in the medium, okay? So the speed, the harmonics that you generate are a function of the wave speed. Now, we know this from stringed instruments. If you're tuning a guitar or you're tuning a violin, you tighten or loosen those pegs, those tuning pegs, because by tightening them, you're making the string oscillate faster. You're making the propagation speed higher. By loosening them, you drop it, so you get different notes if you loosen or tighten the string. With wind instruments, it usually involves pulling out a tuning slide or pulling out a barrel or something like that. So you're lengthening and shortening the air column, which also determines the wave speed. How we perceive these different harmonics is as different frequencies or different musical notes. Now, so we know the range of human hearing is about 20 hertz to about 20,000 hertz. Below that, we call that infrasonic, and above that, we call ultrasonic. So like an ultrasound is a frequency that is above the range of human hearing, but it's still a sound wave. It's just not one we can detect. So the two equations that we use to calculate wave speed, the first one is for a string. So you've got a string that has a certain thickness and a certain length. So we combine those together to call that the linear density, or mu, okay? So that's the mass per length of the string. So say if you look at a piano or a guitar, the strings are not all the same thickness, okay? The other part is the tension, and again, that goes back to the tuning peg, tightening or loosening the tuning peg. For us, there is an empirical equation that you can use for the speed of sound that we can, now there's other equations used for speed of sound in gases that you can use, and has to do with the specific heat capacity and the density and on the bulk density and all of that. But a nice, simple empirical equation for the speed of sound in dry air, so indoor air really, or any air really, is 331 plus 0.6 times the temperature in Celsius. And you add those together, and that gives you the speed of sound in meters per second. So there's different systems that we can look at, and the video talks about these a little bit, but we're going to look at two basic systems. One where the ends are symmetric, meaning they're both either complete cancellation, which we call nodes, or complete constructive interference, which we call antinodes. But they're the same on both ends. So like a guitar string or a piano string would be fixed on both ends, so you have a node at either end. Since it's a symmetric situation, you get whole numbers of standing waveforms, or what I call footballs, but whole numbers of standing waveforms. And you can calculate the wavelength of these waveforms by counting how many you can fit in the length, and then you can use that in the wave speed equation to determine the frequency. So if we rearrange the wave speed equation that says speed is equal to the wavelength times the frequency, and we solve for the frequency, it's just the speed divided by the wavelength. So that's how we get to these equations. So if you count the wavelengths, or figure out how to write the wavelengths in terms of the length of the string, and then divide the speed by that, for a symmetric boundary condition, you can use this equation, where the frequency of whatever harmonic that you're wanting to look at here, F sub n, is the number of that harmonic. So the first harmonic, second harmonic, third, whatever, times the wave speed using those two previous equations divided by 2 times the length of the string or the air column. Okay, so the fundamental frequency would be n equals 1. The next one would be 2 times that, 3 times. So you can also write this as the frequency of the harmonics, of the upper harmonics, are always a whole number multiple times the fundamental. So once you set the fundamental frequency, which is given by V over 2L, you set what the harmonics are. And this is part of how we determine music theory and chord building and all of that. Now, if you have a situation where you have an asymmetric boundary condition, where one end is a node and the other end is open, like when you blow across the top of a bottle of water or a Coke bottle, where the Coke bottle is, there's a barrier there. So that stops the oscillation. So that's a node. The other end is open. So the other end of the air column can vibrate as much as it wants to. So I have an asymmetric boundary. I have a node at one end and an antinode at the other. Because of that situation, you've always got half of a standing waveform or half of a football there to start with. So what that means is I can only support odd numbers of harmonics, the odd harmonics. I can't get 2, 4, 6, 8. I can only get 1, 3, 5, 7, and so on. So if you go through and calculate the wavelength there, it turns out you have to do 4 times the length of the string or the air column to get a wavelength. So now for an asymmetric boundary condition, you have odd numbers, so M is odd, divided by V over 4L. Again, V is going to be from those equations for speed. Now this really only happens in air columns, so you would want to use the one for the speed of sound in air. Now, another property of sound that we often talk about is the loudness. Now, when I talk about the loudness of a sound, and I say, okay, this sound has an intensity of 1 watt per square meter, I don't understand what that means really. But if I tell you that same sound has an intensity level of 120 decibels, you have a better understanding that that's a pretty loud sound. So the decibel scale is a way to measure intensity level. Intensity, for us, it has to do with the amplitude. So the loudness of a sound has to do with the amplitude of the wave. So intensity is just the rate of energy transfer, so power per area. So the power is constant. It's set by the source. So the speaker or the person talking or the explosion or whatever it is, it has a certain power output that it's constant. But as it moves away from the source, it spreads out over larger and larger surface areas. We're going to assume sound is what we call a spherical emitter. So you can imagine all these hollow spheres nested together. And as the sound moves out, it spreads out over those larger spheres. So the intensity drops as you move away from the source. And it turns out, because it's spherical, it drops quickly. It drops as 1 over r squared. So it works like spray paint. It's spreading out over an area. If you stand further away from whatever you're trying to spray paint, it spreads out over a larger area and it's less intense. So intensity is watts per square meter, but we can also measure what's called the intensity level using decibels. So the way we convert to decibels, oh, and that's a terrible break right there. The intensity is measured compared to what's called our threshold of hearing, which is the intensity that can be detected by a normal, healthy human ear, which is 10 to the negative 12th watts per square meter. And that's a terrible break there. That should be 10 to the negative 12th watts per square meter. We compare it to that, but it's a logarithmic comparison. And so we take the intensity of our sound here. So this is whatever we're listening to divided by the threshold of hearing. We take the log base 10 of that number, then we multiply that number by 10. So 1 watt per square meter would be 1 divided by 10 to the negative 12th, which is 10 to the 12th. Take the log of that, which is 12. You multiply 12 by 10, and that's how you get that's 120 decibels. And we'll have some examples of that you'll be able to see as we work some example problems. But so the decibel scale is just something that gives our brain something a little more easy to reference than very large numbers like 10 to the negative 12th, or I guess that's a very small number, but lots of zeros. The only time I want to see a lot of zeros is on a check. So my brain doesn't comprehend really big or really small numbers, so we convert it to this decibel scale. Now, another property of sound is Doppler effect. Doppler effect occurs when you've got sources and observers of sound moving relative to each other. So we use this a lot in weather, okay? And let's see if I can find the video of the bats. Oh, shoot, they took it down. Okay, darn it. Oh, well. So Doppler effect happens when you have a source and an observer moving relative to each other. The equations are fairly straightforward, but what the main point is when you've got either a source or an observer or both, their relative motion is toward each other, you will perceive a higher frequency. When they're moving away from each other, you perceive a lower frequency. Now, you know this if you've ever been caught at a train crossing. As the train comes, it sounds like, and it passes you, it sounds like it goes, whoa, like that, or a motorcycle might pass you, or somebody's music is really loud and you can hear it as they pass you. It sounds like the note is changing when it's really not. It's our perception of that note is changing. Okay, and I'll put up a little video that'll kind of show this, how these waves interact. But basically what happens is, say, for example, you have a source of sound that is moving away from you. Okay, so if I'm standing here listening and the source of sound is moving away from me, even though it's giving off sound waves at a regular frequency, as it moves away, each one of those waves has to travel a longer and longer distance to get to my ear. So my ear perceives them as being artificially spread out. So I hear a lower frequency. So when the train passes you and is moving away, you hear that lower sound. Okay, the formula you use depends on what's moving. If the source of sound is moving, then the waves have to interact with the medium differently. If the observer is moving, the sound waves don't have to interact with the medium differently because they're all sitting still doing the same thing, but you're moving through the medium. So there's two different formula in the book that show moving source and a moving observer. Again, this is an apparent change in frequency. If the relative motion stops, you go back to hearing exactly the right frequency or exactly the true frequency. We use this in Doppler radar where you send sound signals into a storm, for example, and what they do is when they get that echo back, if part of the storm is rotating toward you, you hear a higher frequency. If part of the storm is rotating away from you, you hear a lower frequency. So what they look for is those signatures close to each other in close proximity. Then you can figure out how quickly that rotation is happening, and you can say, oh, there's rotation in the storm, or oh, there's a radar indicated tornado or whatever. So Doppler radar has really revolutionized how we study tornadoes, for example. Okay. So this can create a phenomenon called beat frequency, where beat frequency happens due to interference, where you take two sounds that are pretty close together and you beat them together. So what you get is you get a secondary sound that causes an amplitude modulation where the sound gets louder and softer and louder and softer. And if you've ever tuned a guitar by pushing down on the 5th fret on one string and then playing the next one up, you hear that vibration or that modulation. Let me see if this video will work. Okay, so this is an example of a beat frequency. This is sort of a visual representation of it. So you've got two different waves of different frequencies, and what you get if you take this wave and you add them together, notice how they're slightly different frequencies. They will constructively and destructively interfere. So where they constructively interfere, you get a larger amplitude, then it decreases to almost nothing, and then it goes back up, and then it decreases to almost nothing, and it goes back up. So this is a visual representation of that, where you've got the two different waves of slightly different frequencies. And so these areas where you see these rings, these are the beats. So you would hear this loudness and softness and loudness and softness. Well, in our everyday world, and the reason we have the cop car picture here is because this is how sirens work. Okay, this is how sirens work. Now, a 2-beat frequency doesn't tell you which frequency is higher and lower. It just tells you the absolute value of the difference between them. But sirens on like fire engines or cop cars or whatever, you've got two frequency generators that beat together, and that's what creates the sound of the siren getting louder and softer and louder and softer. And they can be tuned so that you get a distinct siren for cops versus ambulance versus fire department or whatever. Okay. All righty. I think that's everything. So I am going to stop sharing my screen and turn off the recording, and I hope you enjoyed this.